Let's get things started with another gorgeous image of a galaxy. There's so much to see in this image. The spiral arms tightly wound around the bulge, the dust lanes between them, the glittering blue stars on the outside. It's just magnificent. Here's another galaxy called M87, an elliptical galaxy. Seems kind of dull by comparison, doesn't it? But look closely. Near the center is a tiny blue streak. It might look just like a glitch in the image, but it's not. A closer look shows that there's something extraordinary about this galaxy. The center is glowing brightly, and it's emitting a beam of light. M87 is an example of an active galaxy. There's a supermassive black hole at the center, just as there is in all big galaxies, but what's different here is that the black hole is actively accreting gas. Gas is funneling toward the black hole. The gas slowly loses energy and angular momentum, causing it to spiral inward and speed up and heat up. By the time it's within a fraction of a parsec of the black hole, it's glowing brightly. After it crosses the event horizon, we never see it again, and the black hole gets slightly more massive. But just before that, at the innermost edge of the accretion disk, two powerful jets of plasma are being launched up and down, perpendicular to the disk. Why this happens is only partly understood. One thing that's clear is that the force propelling the jets is electromagnetic. By this point, the gas is a hot ionized plasma, and like many plasmas, it's prone to developing a tangled internal magnetic field. As the plasma and magnetic field approach the black hole, they whirl around in a frenzy, inducing electric fields that can accelerate charged particles vertically. The electromagnetic field becomes so strong that electrons and positrons emerge spontaneously out of pure energy, a phenomenon called pair production. Positrons are the antimatter equivalent of electrons, same mass but opposite charge. All those newborn charged particles fly away from the disk at nearly the speed of light. And the underlying energy supply for all these fields and particles might be the black hole itself. Black holes can rotate. Accreting black holes absorb so much angular momentum from the spiraling material that they probably rotate close to the speed of light. This leads to a relativistic effect in which the surrounding space starts spinning too. And if there's plasma there, the rotational energy can be converted into magnetic energy. So the jets of an active galaxy might be rotation powered, in the same way we saw the luminosity of the Crab Nebula comes from the rotation of the neutron star at its center. Now, none of this is obvious. This so-called Blandford-Znajek mechanism relies on concepts from plasma physics that we haven't discussed. And by itself, it doesn't explain why the ejected particles end up forming such a narrow beam. To explain that, theorists figured that the accretion disk, it's not like a thin, flat plate surrounding the black hole. It's more like a fat inner tube, or a torus, which restricts the escaping charged particles to narrow cones surrounding the black hole. There are many different types of active galaxies that go by different names, depending on how luminous they are and from what angle we're viewing them. For example, an optical image of Cygnus A shows a galaxy with an irregular shape. When we look with radio and X-ray telescopes, we see the galaxy is surrounded by a haze of X-rays, and at radio wavelengths, we see two jets that puff out into galactic-scale fireballs. This type of active galaxy is called a radio galaxy, or to be persnickety, it's a Fanaroff-Riley Class II radio galaxy. Other active galaxies look more prosaic. This Hubble image shows two stars, along with some galaxies in the background. But in fact, the star in the middle of this image isn't a star. It's an active galaxy, millions of times farther away than the star. The giveaway is the spectrum, which shows emission lines from the hot gas in the accretion disk. The accretion disk, in this case, is 100,000 times more luminous than all the stars of the galaxy put together. With that bright light shining in our faces, we can't even see the galaxy. This kind of active galaxy is called a quasi-stellar object, or quasar. How can the light from the accretion disk overwhelm an entire galaxy's worth of stars? And how long could such a beacon possibly shine before it runs out of energy? Let's figure it out. First, we need to remember why accretion disks glow. Gravity pulls the gas inward, speeding it up, converting gravitational potential energy into kinetic energy. Then, within the vortex of material, a lot of that kinetic energy is dissipated as heat. When a small mass, dm, falls from far away, the energy released is gm times dm over 2r, where in this case m is the black hole mass and r is the inner edge of the accretion disk, which is about 3 times the Schwarzschild radius. That's the location of the innermost stable circular orbit, the ISCO, as you might remember from our initial foray into black hole physics back in Lecture 7. To calculate the resulting luminosity, energy per unit time, we divide by the time interval, dt, over which the mass is falling, and then simplify. The answer is 1/12 dm dt times c squared. Then let's solve for dm dt. That's the rate at which the black hole must be fed in order to produce a given luminosity. An entire galaxy has a luminosity of order 10 billion suns, and if the accretion disk is 100,000 times brighter, then L is 10 to the 15 solar luminosities. What value of dm dt is required? The answer is 5.1 times 10 to the 25 kilograms per second. That sounds like a lot, but is it? Let's convert it to more relevant units, say solar masses per year. Numerically, that comes out to be 810. So it's not so much after all. The Milky Way is not currently an active galaxy. Our black hole, Sagittarius A star, is in between meals. But all big galaxies, including our own, go through phases of activity and inactivity, depending on the supply of gas to the central black hole. There's evidence that the Milky Way was last active a few million years ago. It's based on a gamma ray image of the entire sky made by the Fermi Space Telescope. There are 2 regions of excess gamma rays, above and below the center. They're interpreted as the fading bubbles of high-energy particles that were spewed out by the relativistic jets during an episode of accretion sometime during the Pliocene epoch here on the Earth. Active galaxies might be part of the explanation for a pattern I showed you last time, the connection between the mass of a black hole and the mass of the surrounding galaxy. When a galaxy grows by accreting a smaller galaxy, the central black hole feasts on the fresh supply of gas. And then the powerful jets from the newly activated accretion disk push back on the infalling gas, expelling it, or at least preventing it from accreting. So in this scenario, galaxy growth is self-regulating. If the galaxy starts growing too fast, the black hole gets out of control, producing outflows that put the damper on any further growth. This type of negative feedback between the black hole and the surrounding galaxy could explain why their properties are linked so tightly. Okay, it's time to zoom out again, to scales beyond individual galaxies. We've seen that wherever we look, we see galaxies. Farther we look, the more we see. What I want to show you now, though, is that galaxies don't have totally random locations. They're clustered. If you start in one galaxy, you're more likely to find another galaxy within a few megaparsecs than if you'd started at a random point in the universe. You can see that in an all-sky map of the locations of the brightest galaxies. If galaxies were sprinkled randomly, the map would look like static. But it doesn't. The galaxies are clustered. Their distribution has a distinct texture, like a sponge or a bunch of spider webs. The largest structures on the all-sky map encompass hundreds of thousands of galaxies. We call those superclusters, and the relatively empty regions are the voids. On the other end of the spectrum, we have little groups of a few dozen galaxies, including ellipticals, disk galaxies, and merging galaxies. We also see clusters with hundreds or thousands of galaxies. In these big clusters, ellipticals tend to outnumber the disks, presumably because in dense clusters there's a greater probability for the sort of galaxy collisions that produce ellipticals. A galaxy cluster is a gravitationally bound system, with each galaxy following a complex orbit determined by the combined gravitational potential of all the galaxies in the cluster. As we learned last time, we can use the virial theorem to estimate the mass of the entire cluster. This was first done by an astronomer, Fritz Zwicky, in the 1930s, in his study of the Coma cluster. He obtained spectra of individual galaxies and saw some were redshifted and some were blue-shifted relative to the average. From the spread in these Doppler velocities, he measured the velocity dispersion to be 1,000 kilometers per second. He also measured the cluster radius so he could estimate the mass using the formula we derived last time. The answer he got was about 5 × 10⁻13 solar masses, which was very strange. The Coma cluster has about 1,000 galaxies. So Zwicky's calculation implied the average galaxy mass is 5 × 10⁻10 solar masses. But based on the luminosities of the individual galaxies, his best estimate for the average mass was only a few times 10⁸. In other words, the mass of the cluster seemed to exceed the sum of the masses of all the stars within the galaxies by a factor of 100. This was the first clue that the overwhelming majority of the mass in the universe is not luminous. There's something in the Coma cluster exerting gravitational forces on the galaxies, making them move fast. But we don't know what. We do know it's invisible at all wavelengths. It's dark. This is the famous dark matter problem. The numbers have changed since Zwicky's day. These days we think the dark matter outweighs normal matter by a factor of 5 or 6. And we have lots of other evidence for dark matter too. Starting in the 1970s, it became clear that dark matter pervades individual galaxies too, and not just the spaces between them. For an elliptical galaxy, we can estimate the total mass in 2 ways. One is by measuring the velocity dispersion of the stars and using the virial theorem. The other is by measuring the total luminosity of the galaxy and calculating what total mass of stars is needed to produce that much light. The virial mass always exceeds the luminous mass by a large factor. We can perform a similar test with disk galaxies. We perform Doppler spectroscopy of the starlight at different distances from the center of the galaxy. That way we determine the rotation velocity as a function of radius. That function, v of r, is called the galaxy's rotation curve. What would we expect the rotation curve to look like? Let's start simple. We'll pretend, contrary to fact, that the galaxy is a point mass, m. Then the situation is just like a planet going in a circle around a star. We set the centripetal acceleration equal to the gravitational acceleration and solve for v, giving root gm over r. So we'd expect the rotation velocity to decline with increasing radius. A real galaxy, though, doesn't have a central dominant point mass. Remember, the black hole is tiny compared to the combined mass of all the stars. So we need to calculate the gravitational force from the whole distribution of mass within the galaxy. And here things get tricky. Newton taught us that if we're at a distance r within a spherical mass distribution, we're allowed to ignore all the exterior mass and pretend the interior mass is lumped together as a single point at the center. That's a relatively easy problem to solve, and Newton proved you get the same answer as you would by solving the harder problem of a spatially extended mass distribution. But disk galaxies aren't spheres, they're disks, and Newton's theorem doesn't apply to flat disks. For a disk, the formula for the rotation curve is much messier. We would need to do integrals involving modified Bessel functions of the second kind, and we're not going to do that. We'll do what astrophysicists tend to do. We'll assume the galaxy is a sphere anyways, and we'll trust that the answer will resemble the right answer, even if it differs in detail. We'll describe the mass distribution with a function, m sub r, that tells how much total mass is enclosed within a sphere of radius r. That same kind of enclosed mass function was useful when we were modeling the interiors of stars using the equation of hydrostatic balance. As r increases, m sub r rises too, since we're enclosing more and more material, until we get far enough away that we're enclosing all the mass. Then, in the limit of large r, m sub r would level off to a constant, the total mass of the galaxy. To find the velocity of an orbiting star, we appeal to Newton's theorem. We simply take our previous result and replace the constant m with the function, m sub r. Now, back to the story. In the 1970s, measurements of galaxy rotation curves got more accurate and extended to larger r. Nearly everyone expected that m sub r would level off once r was larger than about 10 kiloparsecs. That's outside the visible disk of stars. That far away, m sub r should stop increasing, and the rotation velocity should start declining as 1 over root r. But that's not what was observed. Instead, v was found to keep rising. In many galaxies, it levels off to a constant value, but it doesn't go down, even well outside the disk. What does this mean? If v is observed to be a constant, then we can solve for m sub r, and we find that it grows in proportion to r. Way out there, where there are hardly any stars, as we increase r, we still enclose more and more mass. It's the dark matter again. More sophisticated analyses, using the best available data, show that the dark matter does in fact form a nearly spherical mass distribution, and it extends out to hundreds of kiloparsecs. We're led to the stunning conclusion that a spiral galaxy is just a little bit of flotsam spinning around at the center of a much larger and more massive entity, which has been called the dark matter halo. What is the dark matter? It's one of the most important unanswered questions in astrophysics. Astronomers and physicists have tried for decades to detect dark matter in some other way besides its gravitational influence, and they've failed. Theorists have tried to dream up new forms of matter that could avoid detection in all these ways. All of this work has narrowed down the possibilities for dark matter, and I wish we had time to examine them all, including asteroids, cold hydrogen gas, brown dwarfs, neutrinos. I would show you how they've all been ruled out. But given our limited time together, I'll simply say that the idea currently in favor, basically the only one that hasn't been ruled out, is that dark matter is composed of one or more hitherto unknown fundamental particles. Particles that feel and exert gravity, but that otherwise interact very weakly, if at all, with normal matter. No electromagnetism, no nuclear forces. The dark matter problem is kind of embarrassing. When I tell my non-astrophysical friends that we think most of the matter in the universe is in an unknown, mysterious form, they are often understandably skeptical. My father teases me about it all the time. For similar reasons, the dark matter problem attracts a lot of amateur physicists who think this is their opportunity to prove Newton and Einstein were wrong. Maybe we just need a new theory of gravity. Maybe the equations are simply inapplicable to describe forces ranging over spatial scales of kiloparsecs or larger. You might be tempted to follow this path too, and it might be the right one. Let me warn you, though, that many have already gone down this path, including very talented professional physicists, and concluded it's a dead end. The accumulating weight of the astronomical evidence and the failures to find new equations that work without any dark matter suggests to me that inventing a new fundamental particle is at this point less crazy than tinkering around with the law of gravity. Before this lecture ends, I want to show you one more thing about galaxies, something that will set our agenda for the rest of the course. We can measure how fast a galaxy is moving toward or away from us from the Doppler shift. The fractional shift in wavelength is equal to the radial velocity divided by the speed of light. If the wavelengths are being stretched to larger values toward the red end of the spectrum, delta lambda is positive and the galaxy is moving away from us. Likewise, if the spectrum is blue shifted, the galaxy is coming toward us. When we do this for the few dozen brightest galaxies in the sky, we find the radial velocities are all over the place. Andromeda and Triangulum are coming towards us, others are zooming away from us. But when we do this for fainter galaxies, a strange thing happens. They're almost all redshifted. They're all speeding away from the Milky Way. This was first discovered by Vesto Slipher in the early 20th century. It's curious, but it gets even more interesting when we measure the distance to each galaxy. That's a lot harder. Remember, reckoning distances is traditionally the hardest part of astronomy. One way to do it relies on Cepheid variable stars. Remember them? Cepheids pulsate, glowing brighter than fainter with a regular period. And the period is found to be closely linked to the luminosity. So if we can measure the period, we can calculate the luminosity. They act as standard candles. So we can use the flux-luminosity relationship to solve for the distance, d. But individual Cepheids can't be detected beyond about 50 megaparsecs. To reach out further, we use standard explosions, type 1a supernovae, which always seem to explode with about the same energy, or at least nearly the same. They're predictable enough so that if you measure the color and the duration of the afterglow, you can calculate its luminosity to within a few percent. And their great advantage is that they're bright enough to see all the way across the universe, billions of light years away. When we measure radial velocities and distances to lots of galaxies and plot one against the other, we see an obvious pattern, a straight line. V is proportional to d. A diagram of this type, published by Edwin Hubble in 1929, was the first clear evidence for the Big Bang. That's because V proportional to d is what you expect from an explosion. To see that, let's imagine we have a bunch of particles at a single location at time zero. Then there's an explosion, imparting each particle with a random velocity. Some particles are shot out at high speed, others at lower speeds. At some later time, where will each particle be? Well, the higher the speed, the farther it will get. Distance equals velocity times time. So at any given time, we'll observe d and v to be proportional. To be more formal about it, in a way that'll help us later on, suppose that the ith particle has a velocity v sub I. The distance it travels between time zero and the present time, t naught, is vi times t naught. That implies vi equals ri divided by t naught. Velocity is proportional to distance, and the constant of proportionality, the slope of the line in Hubble's diagram is 1 over the time since the explosion. That slope is called the Hubble constant, and it's denoted h0. Its value is about 70 kilometers per second per megaparsec. Taking the reciprocal and converting megaparsecs to kilometers and seconds to years gives a value for t0 of 14 billion years since the Big Bang. That agrees well with the best estimate of 13.8 billion years that comes from more sophisticated analyses. But that's partly a coincidence. We'll see in the lectures to come that the story isn't as simple as galaxies coasting away from a single point. Their velocities need not be constant. After all, gravity acts to slow the galaxies down and bring them back together. For now, though, I'd like to answer a question that occurs to everyone upon seeing the Hubble diagram for the first time. Why are the galaxies rushing away from us? Does that mean that we're sitting at the center of the universe, the location of the Big Bang? That seems wrong, and it is. The Hubble diagram doesn't imply that there's any sort of privileged galaxy at the center of the universe. Edwin Hubble would have published a similar diagram no matter which galaxy he lived in. A helpful analogy is with raisin bread. You're inside a lump of dough sitting on a raisin, with other raisins all around. The oven comes on, and the dough expands, the bread rises. You'll see all the other raisins receding from you with a velocity proportional to distance. And here's the point. If you hop over to a different raisin, you'll still see all the other raisins receding from you with a velocity proportional to distance. There's no unique center of the expansion. And if the crust of the bread bothers you, we don't see any crust in the universe, then just imagine that the loaf is so enormous that the boundary is too far away to be detected. You might not find this baking analogy completely persuasive, so I'd like to prove the result more formally. Our universe is filled with a large number, a potentially infinite number, of raisins, or galaxies, each with a position vector r. One day we measure the positions, Ri, and the velocities, Vi, of all the other galaxies. We use a coordinate system in which our galaxy, the Milky Way, is at the origin. We discover the Hubble expansion, Ri equals Vi times t. Then let's say you build an intergalactic spaceship and fly to a different galaxy, say galaxy number 1, and I will stay put. You remeasure the distances and velocities of all the galaxies relative to your new home galaxy in a coordinate system where galaxy 1 is at rest at the origin. Let's call those new data R' and V'. What will be the relationship between them? We can deduce it using vector algebra. Ri' is the vector going from galaxy number 1 to the ith galaxy. That's equal to Ri minus R1. As for the velocity, whenever I measure a velocity Vi, you measure Vi minus V1, since you're moving along with galaxy 1. So Vi' equals Vi minus V1. Now let's take the R' equation and replace the R's with VT's based on the Hubble relation observed in the Milky Way. We factor out the T, and then we recognize the vector in parentheses as Vi'. We thereby deduce that you will find Ri' equals Vi' times t. Your measurements too will show that velocity is proportional to distance with the same proportionality constant. Everybody, everywhere, draws the same conclusion. But wait a minute. What happens if we turn back the clock? The galaxies come closer and closer together, so doesn't that mean they'll all land on a single point? Not necessarily. For one thing, The theory of general relativity describes the Big Bang as the expansion of all of space from a condition of infinite density, not an explosion that took place at a single location. Or in the world of baking, we need to imagine an infinite loaf of raisin bread. If we reverse the clock and watch the bread unrise, the raisins get closer together, but it's still infinite in all directions. We just bring in more and more raisins into our field of view, and the bread gets denser and denser until at time zero, it's infinitely dense everywhere. Okay, enough about raisin bread. In the last couple of lectures, we'll improve upon our model for the Big Bang. We'll examine independent evidence that the universe was once hot and dense. We'll add the effects of gravity and general relativity, and we'll discuss the implications for the early universe and for the distant future.